Hello everyone, welcome to the first part of proof strategies. The plan for this lecture is as follows. We will introduce various proof strategies that we will be encountering in this course, namely direct proofs, and we will see some forms of indirect proof, namely the proof by contrapositive, vacuous proof and proof by contradiction. So, several form of theorems often involve a statement of the form. You have to prove that you have to prove an implication which is universally quantified. Say you have to prove statement of the form that for all integers x, if x satisfies some property, then it has these conditions or these extra properties and so on, right. So, those statements will be represented by this universally quantified implication, and you need proof mechanisms to prove universal quantifications of this form. So, how do we prove a universally quantified implication? We can't take each and every x value in the domain and check whether p of x implies q of x is true or not if my domain is infinitely large. And that is why in the last lecture we saw that you can apply universal generalization to prove universally quantified statement, namely you can pick some arbitrary element c from the domain where c has no extra property, you do not know anything about c, it is just some arbitrary element, and you show that the implication p of c implies q of c is true. If you show that this implication p of c implies q of c is true, then based on universal generalization you can conclude that this universally quantified implication is also true. That means, now our problem boils down to proving statements of the form a proposition implies another proposition, because p of c is a proposition, q of c is also a proposition, because we have substituted x with c and we want to prove whether this implication is true or not. So, now our goal will be to see various proof mechanisms for proving statements of the form p implies q, where both p and q are propositions. So, we will start with the direct proof method. As the name suggests, it is direct because in this proof method we start assuming that my premise p is true, and logically I show that my conclusion also will be true. That is why this method is called a direct proof method. A very simple illustration of this proof method is the following. Say I want to prove the statement that if n is an odd integer, then n square is odd. First thing that you have to understand here is that this statement is about all integers n. Even though the word all is not explicitly given here, this is a universally quantified statement, and say O of n is a predicate which is true if and only if n is odd. Okay. So, the statement that I want to prove here is the following: O of n implies O of n square is true for every integer n in the domain, and I want to use a direct proof method. So, what I do in the direct proof method, I assume my premise to be true. So, I pick some arbitrary integer n here and assume it is an odd integer. Under that assumption, I have to show that the square of the same odd integer is also odd. Okay. So, since n is an odd integer, I do not know the exact value of n, that is important, right, because it is an arbitrarily chosen element from my domain. But since it is odd, I know that I can write it in the form 2 times k plus 1, where k is also some integer. It could be positive, it could be negative, depending upon what is my n. Now, if I take the square of the same n by rearranging the term, I get n square is of this form, and now if I substitute 2 times k square plus 2k by another integer k dash or k prime, then I come to the conclusion that n square is 2 times some integer plus 1, meaning n square is also odd. That means, starting with the premise, I can directly come to the conclusion, and that is why this is a direct proof method. However, it turns out that it is not always possible to directly prove that p implies q is true. Okay. And for situations like that, we need to have mechanisms which are indirect, right. We still want to prove p implies q, but not based on the direct proof method, and there are various proof mechanisms under this category of indirect proof. Okay. So, we will see each of them, and as I said, where indirect methods are used where we cannot apply the direct method. Okay. So, for instance, if I want to prove the statement that for all integers n, if 3 times n plus 2 is odd, then n is odd, then I can't prove this statement using the direct proof method, even though this statement is true. Because if I start with a direct proof method, I will say let 3n plus 2 be odd, okay, where n is arbitrarily chosen. Then you can say that 3n plus 2, since it is odd, it is some 2 times k plus 1, and after that I do not know how to proceed and come to the conclusion that n is also odd. My proof might become very complicated. So, that is why I need additional methods here, which are indirect methods. So, let us see the first indirect method, which is called proof by contraposition, and the idea behind proof by contraposition is the following. Your goal is to prove the validity or the fact that P implies Q is true. We do that by instead showing that negation of Q implies negation of P is true. And why this is a valid proof method? Because we know that P implies Q is logically equivalent to negation Q implies negation P. That means, both P implies Q as well as negation Q implies negation P takes the same truth value. If P implies Q is false, then so is negation Q implies negation P. If P implies Q is true, then so is negation Q implies negation P. Okay. So, now let us take the same example which we discussed in the last slide. We want to prove that if 3n plus 2 is odd, then n is odd for every integer n, and we want to prove it by contrapositive. So, what is the P part here? The P part here is if 3n plus 2 is odd, the Q part here is n is odd. That is what you want to prove. What will be negation of Q? The negation of Q will be n is even, and what will be negation of P? Negation of P will be 3n plus 2 is even. So, now our goal will be to verify the implication in the reverse direction. Okay. We want to verify that if n is even, then can we come to the conclusion that 3n plus 2 is also even. If we can prove that, then that is equivalent to proving our original implication. So, now I assume n is an even integer, and it is arbitrary. Why arbitrarily? Because we are still applying universal generalization, because we are now trying to prove an implication which is universally quantified. Okay. So, I can't take each and every n in the domain and prove this implication. That is why I am taking an arbitrary n which is an even number. Since n is arbitrary, but I know it is even, I can write it in the form 2 times k, where k is some integer which could be either positive or negative, and then it is easy to see that 3n plus 2 can also be represented as an integer of the form 2 times k prime, where k prime is some integer, right. And hence, my implication in the contrapositive direction is correct, true, and that is why my original implication is also true. So, now you can see the proof is so convenient. Okay. There is another indirect proof method for proving P implies Q, which is called vacuous proof, and this is based on the idea that your implication P implies Q is always true if P is false, irrespective of what is Q. Q could be true, Q could be false, it does not matter. If your premise P is false, then definitely P implies Q will be true, right. So, for instance, imagine P of n is a predicate which is defined over the set of integers, okay, and P of n represents the statement that if n is greater than 1, then n square is greater than n. That is the definition of P of n. Now, we want to check whether P of 0 is true or not, right. So, remember P of 0 is now a proposition which is obtained by substituting n equal to 0 in your predicate P of n. So, what is the proposition P of 0? The proposition P of 0 is if 0 is greater than 1, then 0 square is greater than 0. So, this is your P part, this is your Q part. You want to prove P implies Q is true or not. So, now if you check the P part, it is a false proposition, because 0 is not greater than 1. Then it does not matter what is q, whether it is true or false. In fact, in this case q is false, the overall implication is true, because false implies false is defined to be true. That is the truth value of implication. That means, I can say that the statement p of 0 is vacuously true, because the premise is false and it does not matter what is the conclusion. Even though the conclusion is false, the overall implication is a true statement here. So, here I am using a vacuous proof method. We can prove P implies Q even by contradiction method, which is an indirect proof method for proving P implies Q, and this is based on the idea that P implies Q is logically equivalent to P conjunction negation Q implies false. Okay. You can easily verify that. You can draw the truth table of P implies Q, and you can draw the truth table of this RHS expression, and both the truth values both the truth tables are same. Okay. So, the idea here will be that if our goal is to prove that P implies Q is true, then instead of assuming Q to be true, you assume that negation of Q to be true and add it to the premise P and come to the false conclusion. If that is the case, then that is equivalent to showing that indeed Q follows from P. That is what is the basic essence of this proof method. Okay. So, for instance, if I want to prove the statement that if 3n plus 2 is odd, then n is odd. We had already proved it by proof by contrapositive, but let us see a proof by contradiction method. So, this part is your P part, this part is your Q part, okay. And the proof by contradiction will proceed as follows. So, you are assuming P to be true, but you are assuming Q to be false. Assume Q to be false, and then based on these two statements you have to come to a false conclusion. If you do that, that means whatever you assumed about Q is not correct. That is what is the essence of this proof by contradiction method, right. So, since you are now assuming n to be even, that means n is some 2 times k, and since n is arbitrarily chosen, right, because we are proving a universally quantified statement and we have chosen n to be arbitrary because we are applying the universal generalization here. So, we do not know the exact value of n except that it is an arbitrarily chosen even integer. So, that is why n will be some 2 times k, and that gives us the conclusion that 3n plus 2 is even. Okay. So, now you can see that how do we get a contradiction here. Okay. So, we started with the premise 3n plus 2 to be odd, and we assumed n to be even. Based on these two premises or these two statements, I come to the conclusion that 3n plus 2 is even. How can that be possible simultaneously, that 3n plus 2 is odd as well as 3n plus 2 is even? That is not possible simultaneously. These two things can't exist simultaneously. That means the problem due to which this situation has occurred is because you made this incorrect assumption that n is even. Okay. That means n has to be odd, and that shows that P implies Q is true, and this follows this structure, right. So, P was the statement that 3n plus 2 is odd. To that you added the negation of the conclusion, namely n is not even, and based on these two things you come to a false statement, a false situation that both 3n plus 2 is odd and 3n plus 2 is even, right. That means both P and negation P, which is not simultaneously possible, which is, that means this is P and this is negation P, which is equal to false. So, you come to the false conclusion. Okay. It turns out that we can use the proof by contradiction method even to prove that a single proposition P is true. So, we used proof by contradiction in the previous slide to prove the truth of an implication, namely P implies Q, but you can use the proof by contradiction method even to prove that a single statement P is true. Okay. And this is based on the following idea. This is based on the idea that negation of P implies conjunction of R and negation of R is logically equivalent to negation P implies false. That means, your goal is to show P is true, but in this proof method what we do is we instead assume that P is false, and if we assume P is false, then we have to show that based on that we come to a false conclusion. That means, we come to a scenario where both R as well as a statement negation of R is true. And if that is the case, that means if negation of P implies false is true, then that can be possible only if P is true, right. Because if P is if negation of P turns out to be true, then true implies false can never be true. So, the only way negation of P implies false can be true is if negation of P is also false, and if negation of P is false, that means my statement P is true. So, that is the proof mechanism here, right. So, you start with a negation of whatever you are supposed to prove, and from that you should be able to logically show that both a positive statement and a negative statement simultaneously can be derived. Okay. So, let us see how this proof method is applicable to prove that root 2 is irrational. Okay. So, what I do here is, this is the statement P that I want to prove. My proposition P which I want to prove here is that root 2 is irrational. I assume a negation of that. That means, on contrary, I assume that the root 2 is rational. That means, I am now assuming negation P is true, and based on that I have to come to a false conclusion. That means, from negation P I have to come to a false statement, which will show that P was actually true. Now, since root 2 is since I am assuming root 2 to be rational, that means I can express it in the form A over B, some integer A over some integer B, where the greatest common divisor of A and B is 1. Okay. That is the definition of a rational number. And say this statement is R. Okay. That means, from negation of P I have derived a statement R. I will show that from the same statement negation P I will derive the conclusion negation of R, which will establish that negation P is not possible. So, let us see how we can derive negation of R as well from negation of P. So, since root 2 is of the form A over B, by taking square on both sides I get A square equal to 2B square, and now if A square is equal to 2B square. So, A square is equal to 2B square means A square is even, right, because it is 2 times some integer B square. Then if A square is even, I can prove that A is also even. So, I am not separately proving it, you can easily verify this, that if A square is even, it implies A is even. You can easily verify that. You can prove it by contrapositive. You can show that if A is odd, then A square is also odd. Okay. So, I am not separately proving that. So, I come to the conclusion that A is even, and if A is even, then I can write it in the form 2 times some integer C. Now, if A is some 2 times C, then I get that B square is also some 2 times C square, right, because if A is 2C, then A square will be 4C square. So, 4C square is equal to 2 times B square, that means B square is equal to 2 times C square. And now, if B square is 2C square, then by applying the same property here, that if B square is even, I can prove that B is also even by applying the same rule here. So, say B is even and B is even, that means B is some 2 times an integer D. But if A is some 2 times C and B is some 2 times D, right, that means what can you say about the GCD of A and B? The GCD of A and B will be definitely more than 1. In fact, 2 divides both A as well as B, because both A and B are even. That means, I can say I can come to the conclusion that GCD of A and B is not 1, and that is the negation of R, because R represented the statement that GCD of A and B is 1, whereas negation of R represents that GCD of A and B is not 1. So, you can see that now assuming negation of P, namely the statement which I wanted to prove, I can logically conclude that root 2 is some A over B, where GCD of A of B is 1, and simultaneously I can conclude that root 2 is some A over B, where GCD of A of B is not 1, which is not going to happen. How can it be possible that both R as well as negation of R holds, and R and negation of R means false. That means, from P you can come to the false conclusion. That means, we have showed here that negation P implies false is true. If this is true, this is possible only if P is true. Okay. So, that brings me to the first end of this lecture. In this lecture, we introduced various proof methods. Our main motivation is to prove implications, because we often encountered universally quantified implications, and to prove that by applying universal generalization we have to prove implications involving propositions. So, we have introduced a direct proof method for proving implications, and we have seen some indirect proof methods like proof by contrapositive and proof by contradiction and vacuous proof method to indirectly prove whether P implies Q is true or not. Thank you.